Welcome to this video on embedded development. It's actually my first video on embedded programming. I wanted to make more so a reference for myself, but this could potentially help anyone else that is starting to get into embedded software. I'm going to be focusing on some bare metal programming for the STM32 family of microcontrollers, specifically handling interrupts on a button press. So we will be dealing directly with the raw register addresses and doing all of the bit manipulations and resetting registers to configure all of the GPIO pins and handling the interrupts. So just as a general outline, we're going to wire a button and an LED to the microcontroller. And when a button is pressed, this will trigger an interrupt to toggle the LED. And this will be written, quote, bare metal. So we're not going to be using any libraries or headers besides the essential ones. And this will also get us comfortable with using the datasheets, because we will be referencing this pretty often throughout the entire video, which will be long. I've actually recorded this before, and it took about an hour, but I made a few mistakes and I spent a lot of time debugging, so I decided to scrap it and kind of start the recording over. So I have actually already wrote the code for this, and I will probably throw the repo link in the description. I'm just going to essentially rewrite all of the code that I've already written. But anyways, so there's two setups. We're going to go through the GPIO setup and then the interrupt setup, which is probably will probably take up the majority of the video, because setting up the interrupt takes a little bit of time. But first, we're going to enable the GPIO A and C clock, set up the PC2 as an input pin with the pull-down resistor, because I think most STM32 boards come with built-in weak resistors for pull-down or pull-up, which is pretty convenient. And then I will set the PA1 as an output pin for the LED. For the interrupt, this first step is actually dependent on your board. So, for example, the STM32 F411 black pill, this is a common board I use for most of my projects. You will have to enable the sysconfig peripheral clock. However, for the STM32 WB55, the board that I will be using for this code, there actually is no system config clock. I think it's just enabled by default. So this one will vary depending on your board, and I'll probably show both of the datasheets and the differences because I have both of the datasheets. And then we will enable PC2 for interrupts in the system config register. We will disable the masking for line 2, and this will be in the external interrupt register. Enable the falling trigger in the external register, and then use NVIC to set the priority and enable the interrupt. And then we will finally implement the interrupt function and test it. So that's the quick introduction. Two more things. If you are on Windows, you'll need GNU make. I will be using a makefile, so this is actually optional if you are also going to use makefile. But you can really use any build system or build toolchain you want. I'll be using make and ARM GCC. So if you look at make for Windows, you can download this and get this set up. That way you can run make files. And then you will also need the ARM None EABI GCC compiler, which you can get from the GNU ARM embedded toolchain. And so I already have all of this downloaded and installed. So I would, if you're on Windows, you definitely need to at least have this. The make file is optional, but this is pretty much mandatory. And unless you're using STM32 Cube IDE, then it's not necessary. I actually think they use it internally anyways. So the last thing before we actually get into the project setup and the code, the datasheet I'm using, I already mentioned, I'm using the WB55 board for this video, and my datasheet reference manual is the RM0434. If you are using a different board, I would go ahead and pull up the datasheet. That way you can follow along if you are following along. I got this from st.com, and you can just search for your board's reference manual. So that's pretty much everything we need to get started. What I'm going to do is I'm going to set up the initial project using CubeMX, and the reason why is because CubeMX will generate the makefile, the linker scripts, the setup assembly for the interrupts, and a bunch of convenient things. However, this will also give us a lot of fluff that we don't need, that we will remove. But I would heavily prefer to not write my own linker scripts and makefiles because it's very annoying. So this part is technically optional, but I strongly recommend it that you at least get the project setup from CubeMX, and then we will modify it to our own needs later. So I'm going to use the WB55RG, start the project. Alright, now I'm not going to do any config here. We're just going to go to the project manager. I'll call this interrupt example. And I'm going to select a makefile as my toolchain. If you are on Windows and you don't feel like setting up makefiles and don't want to deal with that, you can also use STM32 Cube IDE, but personally I do not really like Cube IDE. It just feels kind of clunky and slow, which is kind of funny because I use CLion, and sometimes CLion can be a little clunky, but anyways. So, generated the project. Now I got this folder. Let's just open this in CLion. And you can really use any editor. So you can use Visual Studio Code, you can use Sublime Text, CLion, or STM32 Cube IDE. Doesn't really matter. So actually this project right here is the code I wrote earlier that I was talking about when I recorded this video for the first time. But towards the end I kind of ran into some issues I had to fix. So now I am just re-recording this essentially and rewriting all of the code. So let's open our project. Should be in desktop development, interrupt example. Alright, so there's a couple of things that we won't need. So anything HAL related. HAL, if you're not already familiar, is the hardware abstraction layer. It's a relatively popular library for embedded, but we are going to go bare metal, so I'm going to delete it. I actually don't need any of these headers for now, so I'm just going to drop those. We can drop the HAL implementation and the interrupt. I think these interrupts are specific to some of the HAL stuff, so we don't need this. But we do need the system here, so I would not delete this. Or at least I'm pretty sure we need this. I'm going to keep it just to be safe. This HAL driver we can completely drop. And under CMSys, there's a couple things we will need. So this core right here, if you open the datasheet, you'll notice that you have I have a M4 processor, and this kind of corresponds to, like, you have CM0, M1, M2, or M3, M4, so on and so forth. At least I think that's what these are referring to, but I typically just use whatever header corresponds to my processor, so I'll be using core CM4. So we could probably drop most of these, but I will just keep them here because I don't want to accidentally delete anything. And the source is just an empty folder, so I'm going to remove that. And the include here, actually I don't think there's anything redundant here because we do need this header as well. This is the device header that the CM4 header here refers to. So we actually need to include this first and then include the other header. But before we do that, we'll open up this main. Let's remove everything there. We need to do a little bit of makefile setup. So going to delete everything related to HAL and those interrupts that I don't need. I'll keep main and system. We need to keep this startup assembly that contains some very important functions that we will use later. And this will be specific to Windows. If you're on Mac or Linux, you won't have to worry about this, but on Windows, I have had problems in the past if you do not put .exe after these, because Windows will start complaining that it can't find the compiler unless you put the .exe afterwards. So I would recommend doing that. We can get rid of the HAL driver here, keep the device, remove HAL driver, and let me make sure these paths are correct. So I have cmsys include, that looks right, and then I have cmsys device STM32 WB include. Okay, that looks fine to me. And yeah, I think that's all good. So let's reload this makefile, and we will just make sure that this builds before we start writing code. Alright, so let's build. Okay, undefined reference to main. Interesting. Oh, that's because I forgot to actually write the main function. And also, before I forgot this last time. In a microcontroller project, we will need a infinite loop here. Otherwise, when I loaded code onto an MCU without this infinite loop, it kind of immediately executed and then stopped doing anything because it wasn't the application basically stopped running. So I would include that. So now let's build again, and that finished. So momentarily we should see the build folder come in. Sometimes CLine will take a little bit for the project to refresh, but anyways, that will come in soon. But the point is, it did build, and that build folder, whenever it shows up, that will contain the files. Whoops. That'll contain the files that we can use to actually flash the code onto the microcontroller itself, like the ELF, bin, and hex files. So, yeah, we will need the two headers that I pointed at earlier. The first header we have to include is the device header. And after that, we can include the cmsys header. So I'll use the CM4 because I have an M4 processor. And CLine is complaining about my include path, but I can't really be bothered to fix that. I don't really care. So hopefully you can stand staring at these red squiggly lines for a while. And let me try to fix my zoom real quick. Okay, I had to enable a setting to change my zoom level, so now hopefully this is easy enough to see. And you can also see that while I was waiting, the build folder finally showed up, and you can see that we have the ELF file that I can use to flash. And speaking of, I will also be using the STM32 cube programmer to actually flash the code onto the controller, because I think it's very convenient. If you don't use cube, you could use something like OpenOCD, I think is a popular choice, or really whatever works for you. Alright, so now all the project setup is out of the way. We are pretty much ready to get started with the code. So let's take a look at the first task. What we want to do is we want to set up our GPIO pins. So I have PC2 and PA1, which are obviously on GPIO A port and C port. And in order to use those peripherals, we have to enable their clocks. So we will go ahead and take a look at the datasheet. And if you look at your datasheet, you'll have a memory organization or memory map section. And this will give you the peripheral and the base address of that peripheral. So you can see that these are all of the addresses for these different peripherals. One gotcha that you should look for that I actually, this is what caused problems in my first time recording this video, is apparently some peripherals will have two different records, and this first one, this is actually the base address of sysconfig because it's the beginning one, but then sysconfig appears again with a different starting address. And in my first time recording this, I accidentally used this one because I did not see sysconfig showed up twice. So the actual base address for sysconfig is this one right here. So I would be very careful that you actually use the correct base address in case a peripheral, for whatever reason, appears twice. I'm not sure why that is the case, but it caused me about an hour of debugging. So anyways, all of the clock related stuff is in the Rcc register. So let's go ahead and start off by getting the base address for the Rcc. So let's go ahead and add that. We'll define Rcc base with that hexadecimal value. And also, just a side note, Rcc base without the underscore is actually already defined in the device header. However, since I want to completely show how it works really from the ground up using these raw addresses, I'm going to be defining my own macros to hold these addresses and pointers. So I'm going to be prefacing all of these with a underscore because these Rcc base, GPIO base are actually already defined in this device header. Alright, so that's Rcc base. While we're here, we will also need, let's just go ahead and grab a couple of different peripherals that we will need. We will need the external interrupt peripheral, so I'm just going to copy that base address and double check that it doesn't randomly appear anywhere else. Okay. So we'll grab the external interrupt address. And let's grab the GPIO A and C addresses. So this will have an 800 at the end for C GPIO A base, and then GPIO C base. This has an 800. Okay. And let's get sysconfig, the proper sysconfig this time. And this should actually be all of the main peripherals that we will need. Alright, so those are all the base addresses. So now let's get to the, let's take a look at the Rcc registers that will allow us to enable the different GPIO clocks. So if we go to Rcc, we have this register map here, which is useful if you know what you're looking for. But also if you scroll up, this contains some details about the different registers and some of their options and the values of their bits and such. So I already know which register to go to. If you'll see, we have this GPIO-A enable and GPIO-C enable in this AHB2 ENR register. So we can actually just search for that real quick. So here's the AHB2 peripheral clock enable register. And here we have the port A enable, port C enable. And yeah, you can see in the details this is just either enabling or disabling the different GPIO clocks. So, and this has an address offset of 0x04C. So let's go ahead and create a pointer to this address. That way we can dereference and actually modify the content inside of it. So actually I'm going to organize it like this. So all of my RCC stuff will be together. So this is the Rcc AHB2 enable register. Okay, and this will be, so first we will take Rcc base and we will add the offset, which is 0x04C. And right now this is just a arbitrary hexadecimal number. What we want to do is we want to cast it to a pointer, which I will use a uint. Excuse me. I'll use a uint32t pointer, which I'll need standard int for. And typically when you deal with registers, it's a good idea to use volatile, because volatile will essentially hint at the compiler, hey, this data, this underlying data might unexpectedly change. And so it'll kind of, it typically only causes problems if you compile with optimizations, and the optimization might do something funky when you don't want it to do something specific. So typically it's just a good idea to use the volatile keyword when dealing with the registers themselves. And then finally, after we cast it to a pointer, we want to dereference that pointer so we can actually access the underlying data behind it. And so when we do that, we can take this register and we can enable GPIO-A and GPIO-C. And you'll see that writing a 1 will enable the clock. So we have to write a 1, 0, 1 starting at 0 because GPIO-A starts at bit 0 here. And typically, I personally like to use binary literals, but first, even before that, let's just reset. Let's reset those registers. It's typically a good idea before you write anything to kind of clear or reset the registers that you're going to be interacting with, just in case, like, you know, when you're starting up a microcontroller and if it has bits left behind from when you were previously writing to it, and then those registers are still not cleared, and then you can get some buggy behavior, which is actually something that I have personally experienced. It led me to a bug that took me about a half hour to figure out because I wasn't clearing the registers before I was writing to them. So it is typically, I would recommend, obviously it's not mandatory, but I would recommend clearing the registers. So I'm just going to use a binary literal of 000, and I'm bit setting or bit shifting by 0 bits, meaning that I'm just starting at the 0th bit and I'm writing 0, 0, 0 from right to left. So that's what that is. And then after I clear those, we will just write 0B101 because I'm enabling C. So this is GPIO C, this is GPIO B, which is 0 because I'm not using port B, and then this is GPIO A. And we will shift this by 0 bits because we're going from the very right. And I'll just put some small notes here. Let's say reset bits and enable GPIO A and GPIO C clock. And that's pretty much it for that. So we've got this first task done. So now what I want to do is I want to set up PC2 as an input pin with a pull-down resistor, which is our button. So now we actually, we're going to use the GPIO addresses. I'm just going to move this one down a little bit, kind of go in logical order here. So I'll put GPIO C above as well. So let's go back to our memory map, which is page 67 here. And let's go to the GPIO C registers. So we have the mode register. Let's just search for that. GPIO X mode register. And find where it is. Okay. So now here's where we can kind of configure the mode. So 00, which is the default, is input mode, general purpose output mode, alternating function mode, or analog mode. So actually I'm not sure if by default they are 00 or 0 or 11. So I'll just explicitly write 00 just to be on the safe side. And here we got mode 2. So this second register here, these 2 bits correspond to the second pin, and then this mode 1 here corresponds to the first pin. So for GPIO A, I will be writing to these 2 bits here. I'll be writing 01 because it's an output, my LED. And then this mode 2 register here, I'll be writing a 00 to these bits because my PC2 is an input. So let's go ahead and do that. Oh, one more thing. For the mode register, the offset is 0. So the mode register address is actually the same address as the GPIO base. So actually, that doesn't matter. So let's go ahead and define GPIO C mode register, and we're going to dereference cast pointer to GPIO C base, and I don't need to use an offset because it's 0. And I'll do something similar for GPIO A. GPIO A mode register, dereference cast GPIO A base. Alright, so now we will take GPIO C mode register and we will set the bits to 0. So I'll do 0B00 and I have to shift these over. I have to shift these over 4 bits. So I'm taking 00, I'm shifting it over 4, and then from right to left it will write 0 and 0. So let's do that. Shift it over by 4. And this will configure PC2 as input. And then later we will write well, first I'll reset GPIO A, the bits. So I'm going to write 00 to the second bit because I want 0 I want 0, 1 here, but first I'm just going to clear it just to be safe. So now I'll write 0, 1. And notice for GPIO I am resetting these bits, but I also don't need to really write anything here because 0, 0 is already an input. So I don't have to do anything else. But what I do have to do is I have to enable the pull down register, which I'll do in just a second. So I'll just say reset bits and then configure PA1 as output. So now PA1 is pretty much set up. So now we just got to do the pull down resistor, which is one of these registers right here, this pull up down register. And this has an offset of 0x0c. So I'm just going to create a pointer to that real quick. So Gpio pull up down register. Let's create a pointer and dereference. Gpio base plus 0x0c. Alright, so now to actually set that up, we are going to take Gpio pull up down resistor or register, and I'm going to set, let's see, so 0, 0 is no pull up, pull down, 0, 1 is pull up, and 1, 0 is pull down. So pull down is what I want because I want my default state to be 0 when the button is not pressed. And I'll be using this second register right here, which corresponds to the second pin because my pin is on the second line, PC2. So I'll be writing a 1, 0 shifting over 4 bits because I'm starting right here. So this will be, well, yeah, first let's reset it. So 0B00 4, and then I will write 0B10 shifted over by 4 bits. And this will configure pull down resistor on PC2. Okay, so I'll just put some other generic notes here. So setup clocks, GPIO clocks. This will set up PC2 as input with pull down, and then this will set up PA1 as output. So now the GPIO pins are pretty much configured and set up. There's one last thing I want to do with GPIO-A, and when we actually write signals to it, so for example, if I want to turn the LED on or turn it off, we need to use the output data register here. So this ODR, output data register, this will allow us to write different signals to that pin to tell it, hey, I want to turn this on or I want to turn this off. So this has an offset of 0x14, so let's create a pointer to that. We'll say GPIO-A output data register, and this will be GPIO-A base plus 0x14. And right now I'm not going to do anything with it. We'll use this whenever we actually start writing the interrupt function. Alright, so now this is done, and this is done. So now we can actually start setting up the interrupt stuff. So this sysconfig clock, as I mentioned, this is actually not on the WB55 board, but it is on the F411 board. So if I open up that datasheet, I have it right here. Conveniently, I already had this pulled up. So this is the F411 datasheet, and you can see that we have this sysconfig enable in one of the peripheral clock registers, APB2 enable register. So this, if you want to use sysconfig, you have to enable this bit right here, otherwise it will not work. However, on the WB55, which is the board I'm using for this video, I think it is enabled by default and you don't have to actually enable any clocks for it. So the next thing we have to do after you enable sysconfig, if necessary, is we have to enable PC2 to actually handle interrupts, and this is located in the sysconfig, one of these sysconfig registers. So if I go to this memory map here, and I go to sysconfig, so sysconfig right here, so this external interrupt control register, let's just copy, whoops, not sure what happened there, sysconfig external, here it is, external interrupt configuration register. So now this will allow us to enable certain pins to handle interrupts. And my button pin is on PC2, so I'll be using this register right here, which is, I have to write 3 bits to it. And this datasheet conveniently has a guide like this that shows you PA1 or PA2, PB2, PC2. I don't think this is present in every datasheet. For example, on the F411, I do not think that this text is here. Or maybe it is, I actually can't remember. But either way, I need to use this register, which starts at the 8th bit. And if I want to enable PC2, I have to write a 010. So first, of course, as usual, I will first reset this register and just write a 000, and then I will write a 010 starting at the 8th bit. And before I do that, obviously I have to create a pointer to this config register. So let's do that. Sysconfig. Let's move this up a little bit. So this is sysconfig control or external interrupt control register 1. And let's create a pointer sysconfig base plus the offset. Alright, so now let's do sysconfig external interrupt control register 1, and we will reset those 3 bits. So let's write 000, shift it over by 8. And then we will write 010, shift it over by 8. And this will enable PC2 for interrupts. And I'll just put a generic note here, configure interrupts. I'm probably over commenting here, but that's fine. Okay. So now that is one piece of the puzzle here. So now I have to do a couple of things on the external interrupt register. So we have to disable masking, and then we will enable the falling trigger, which is the type of interrupt, but I'll get to that in a minute. So first let's disable the masking for line 2. So if we go to the memory map again, and we find the external interrupt registers, we have a couple of things here. So we have this IMR, which is the input mask or interrupt mask register. Let me just copy this. Okay. So now this will wake up with interrupt request from line X is unmasked. So I believe that this, if I unmask line 2, then this will allow the pins, or this will set up the pins on line 2, so PA2, PB2, PC2, PD2, so on and so forth. This will enable line 2 to basically listen or accept interrupts. At least the way I understand it. Someone can correct me in the comments if I am wrong about that, because this one I am not the most knowledgeable about, this particular register, but I know that it has to be set. So anyways, I'm using pin 2. So all I have to do is write a 1 here to unmask it. But first, let's create a pointer as usual. So let's define external interrupt input mask 1. Get the offset. And first I will reset that bit, so I'll write a 0 and shift it over by 2, and then I'll just write a 1 and shift it over by 2. So now line 2 should be unmasked for interrupts. So now this is done. And then we want to enable the falling trigger. And so there's 2 types of interrupt events. You have, well, actually, I think there's a couple more, but there's two main ones. There's rising trigger, which is from 0 to 1, and then there's falling trigger, which is from 1 to 0. And so when my default state, since I'm using a pull-down resistor, is 0, so my default is 0, I press the button, that goes to 1, and then when I release the button, it falls back to 0. And so basically, if I enable a falling trigger interrupt, when I press the button and release it, whenever I release that button and it goes back to a 0 state, that's when the interrupt is triggered. So in my case, my interrupt will just be toggling an LED. If I press and hold the button, nothing will happen. But as soon as I release that button, then my LED will light up, because I am going to configure a falling trigger, which looks at when the signal goes from high signal to a low signal. So that was just a very quick explanation of what rising trigger versus falling trigger is. But that is configured in right here. This is not the right one. It is right here. So falling trigger selection register, FTSR. Let's just create a pointer to this real quick. All right. And so we want on pin 2 again. And here, if we write a 1, then the falling trigger will be enabled for that input line. So I want to enable falling triggers for line 2. So it'll pretty much be very similar to this actually. So I can just copy this, except I can use the FTSR. And this will enable falling trigger, and this will unmask line 2, and this enables falling trigger on line 2. Alright, so now we are nearly finished. All we have to do is set up the NVIC priority and enable it. So one quick thing, if we actually look at the device header, you'll see that there are some IRQ constants defined right here, and some other interrupt constants. So you can see that we have like the line 0 interrupt, line 1 interrupt, line 2 interrupt, so on and so forth. I'm using line 2 because my pin is on PC2, and so I'll be using this constant, and this is what the NVIC uses. So I'll just say setup NVIC for interrupts. So this will actually enable the interrupt on that line, like finally enable after all of this configuration. I'm just going to copy that real quick. So if we go to the core M4 header file, you'll see that there's two main functions we're going to use. There's NVIC set priority. So there's set priority, which takes the IRQN type, which is the constant I just showed you, and then a priority, which is the value of the priority. And if I am not mistaken, the priority goes in ascending order from most important to least important. So priority 0 is highest priority, and priority 4, for example, is a lower priority than 0. And so if I have two interrupts that happen on the same line at the exact same time, then it will look at their priorities to figure out which one will execute first. And if they have the exact same priority, I'm not exactly sure what will happen, if I'm being honest. I'm not sure if it'll just like choose one randomly. I'm not really sure because I haven't encountered that scenario. But for my purposes, I only have a single interrupt, so it doesn't really matter. I'm just going to set it to priority 0. So I'll say NVIC set priority, make sure I spell it right, and then I will just copy the constant, and I will just set priority to 0. And then finally, to once and for all enable it, we have to enable IRQ and also pass the interrupt line. At least I think that is the function. NVIC enable, yeah, so enable interrupt. Alright, so now the once and final thing, if you look, you have the startup assembly code, and if you kind of go through here, you have all of these weak attributes for some of these functions. And if you have a function with a weak attribute and you implement that function elsewhere, the compiler will take a look at this and it'll say, okay, this thing that has a weak attribute, but I see this function over here that is implemented that is not weak, so I will now use this implementation. And so you'll see that we have these basically the same functions. So we have the different interrupts for the different lines. And so I'm using line 2. So we have to take this exact name. We cannot really name it anything else. I mean, unless you change the assembly code, I guess, but we will implement the external interrupt line 2 interrupt handler. It does not take any arguments. And so now when we press and release the button, this function will get called. And there's one final thing. I know I keep saying this a lot, but when an interrupt gets triggered, a bit is written into a register, and if we want to reset the state of the interrupt, we have to clear that bit. So for example, Well, first, let me just do this so I'm not getting ahead of myself. So when we trigger the interrupt, all I want to do is I want to take the output data register of Gpio A, and I want to write, I'll just say XOR, because I want to toggle PA1. Whoops. So this will toggle PA1. So I'm going to write a 1 and shift it by 1 bit. And the reason why I'm using XOR is because if the button is on and I XOR it with 1, this will give me 0. In other words, it will turn the LED off. If the LED is off and I XOR it with 1, then we'll turn the button on, or it will turn the LED on. So that's why I'm using XOR here. So this is fine. However, if I left the code like this, when I press the button for the first time, the LED will turn on, but it will stay on, and anytime any further button presses will not actually do anything. And that's because we have not cleared the register state after executing the interrupt. So in my what I want to do is every time I press the button, it will turn it on or off depending on the current state. And so in order to do that properly, we have to basically reset the state of the interrupt handler. So if we go back to the external interrupt register, there is this PR register here. So let's just search for that. So this is the pending register, PR1. I'm actually going to make a pointer to this real quick. Alright, so this is the pending register, and we've got some text here. This bit is set, let me make sure that's the right one, yeah. This bit is set when the selected edge event, or in XD, I think this is software interrupt, software trigger arrives on the configurable event line. This bit is cleared by writing a 1 into the bit. So this is the important part. When the interrupt does get triggered, we have to reset the interrupt on that line by writing a 1 into it. That way we can trigger the interrupt again and again because we're resetting it. So once again, I'm using line 2. So after I trigger the interrupt, I want to write a 1 into this bit, into this register, in order to reset the state of the interrupt. That way I can trigger it again. So if I go here, after I toggle a pin, all I have to do is not forget a semicolon, and in the pending register, we will, I will just do an explicit equals because I don't see why not. And I will write a 1 and shift it over by 2. And then this will reset interrupt state on line 2. So I think that is everything. I'm kind of zoom out here. So here's the interrupt. When we press the button, we toggle the pin, reset the state of the interrupt. And then our setup consists of enabling the GPIO A and C clock. We configure PC2 as an input pin. We configure it to use a pull-down resistor, one of the weak inbuilt pull-down resistors. We set PA1 as an output. We enable PC2 for interrupts. We unmask line 2 for interrupts. And then we enable falling trigger for line 2. And then we use the core driver headers to set the priority of the interrupt, and then finally actually enable the interrupt. So hopefully, fingers crossed, I built this correctly and it actually works on my hardware, and obviously no syntax errors. which I did get a syntax error. Let me see here. Volative. That is indeed not volatile. Alright, so out of all of that, I had one syntax error. But now I have this elf file here. So if I open up Cube, I actually don't have a free slot, USB slot, so let me unplug my keyboard real quick. Try to find a slot here, and also try to find my USB. Just give me a second. Okay, so I found the USB, unplugged my keyboard temporarily because I don't have very many USB ports, and let's connect. I have a inbuilt ST-Link, which is convenient, so I can connect my board, and then let's go to our interrupt example, our build, and then our elf file, which was created at 9:55 p.m., which is 2 minutes ago. And let's program this. Alright, so now that has flashed the code onto my controller. And let me just do a quick test. And it does work. So I will load up my, probably just record a video on my phone and append it to the end of this because I don't have any external camera, so let me do that real quick. So here's the actual controller. I have the green wire here, which is the PC2 pin. The red wire is the PA1 pin, which goes into the LED. If I press the button, when I release it, it toggles the interrupt because we have the falling trigger, which goes from a high state to a low state. And I can keep pressing it. Sometimes it's apparently not very responsive, but I can keep triggering this interrupt because remember, every time this interrupt is called, we are resetting the pending register. But yeah, that's pretty much how it works. We have programmed this using the bare raw memory addresses and pointers using the datasheet. So hopefully you learned something about some bare metal programming.